Hello everyone and welcome to our Zeiss-sponsored online seminar called AI-Driven Mineral Analysis, Enhancing Speed and Accuracy. This webinar will provide an overview of the current state of AI applications in geological sciences, with a specific focus on recent advancements in image recognition and analysis. Welcome to our speakers, Dr. Rich Taylor, Geoscience Applications Development, Raw Materials Business Sector, at Zeiss Research Microscopy Solutions in Camborne, UK, and Molly McKilkin, PhD, Business Development Software Solutions at the Carl Zeiss Microscopy Software Center in Rostock, Germany. This broadcast will be recorded and available to watch on demand afterwards. After their presentations, our speakers will be there to answer your questions in a live Q&A session moderated by Dr. Chris Parmenter, Editor-in-Chief of Microscopy and Analysis, so please use the chance to ask anything you want to know in the chat box. And with that, we now hand it over to our speakers and look forward to their presentations.
Hello everyone and welcome to our webinar. I'm Molly McQuilkin. I'm a business developer for the Zeiss Software Solutions, and I'm joined here today by Rich Taylor, who's a senior geoscience application specialist here at Zeiss. And we're going to talk to you today about what Zeiss offers for AI-driven mineral analysis, and specifically how leveraging these AI-based tools for your mineral analysis workflows can allow you to enhance your speed and accuracy. I'm going to get started with some background and insights about how AI-based tools are changing the technology landscape for image analysis and how you can easily use them for your work with the Zeiss products. Then I will pass over to Rich, who will walk through some workflows and examples which have benefited from AI-based analysis tools. So let's get started. I think the best way to start is to discuss what is artificial intelligence, or AI. This is a buzzword within the community, and it's a really powerful tool, but not everyone is familiar with what AI is and what types of AI are relevant for image analysis. If we look at AI in its simplest definition, it's just a collection of techniques that allows computers to mimic human intelligence when performing tasks. Within the category of AI, there are two types of AI relevant for image analysis, which you may have heard of before. The first is machine learning. Machine learning is a branch of artificial intelligence which is based on the idea that systems can learn from data, identify patterns, and make improvements to performance with minimal human intervention. Within the branch of machine learning is another type of AI called deep learning. This is a very powerful AI technique for image analysis in particular, as it uses multi-layered neural networks to mimic complex decision-making processes, and it can recognize complex patterns within data, or in our case, images. Over the years, there has been an uptick in the number of papers published in the geosciences which have begun to leverage AI techniques for image analysis. But why is it that AI is changing the game for image analysis, and particularly in mineral analysis for the geoscience? Well, the reason falls within the nature of the images within this field. If we take a look at a typical mineral image used for mineral analysis, first thing we notice is that there's very close gray levels throughout the entire image, meaning standard thresholds and traditional methods and traditional algorithms normally will not work for proper identification of the different mineral grains and particles. In addition, this identification is often based on unique features within the minerals themselves. That means that simple processes will not be able to repeat and identify these unique features and do accurate identification. As a result of this, currently majority of mineral analysis is conducted using manual identification. And this brings a lot of challenges into the analysis workflow. Not only are these tasks time-consuming, but they are not standardized, and they can allow for the introduction of bias. In addition, since this is a manual process which relies on experts making identifications, it's also not scalable and it's impossible to automate. This is where AI techniques can really benefit in the analysis strategy. AI techniques can learn about these unique features that experts can identify, and it can provide an automated system for proper identification of mineral grains and particles. Now, specifically within the AI family, deep learning tools, and more specific, we'll talk about in a minute, certain types of models within deep learning are really what are needed for accurate differentiation and classification of mineral grains and mineral analysis. So let's take a look at these models. So there's two types of models when we're talking about deep learning that's commonly used for image analysis. And those are pixel-based models and there are object-based models. If we start with pixel-based models, we're going to use an example of two classes, which are cats and dogs. And these models are very good at identifying the structures within the classes. What it is not good at is identifying individuals within these classes. As you can see, we have all the blue area in our class dogs, all the yellow in our class cats, but we do not have individual cats and dogs. Instead, anywhere a cat touches another cat or overlaps, it's considered one structure. What does this mean if we're talking about images for mineral analysis? Let's take an example where we're looking at a low relief mineral here. We have a very nice bright field and sepal image where we can see there are individual mineral grains within this low relief area. If we use something like a pixel-based deep learning method, because these touch, we're going to get something that looks like the yellow here in this image. So we're going to get one unit and not individual grains. Now, that's not to say this isn't a powerful type of deep learning technique. We can use this for another type of example, and it does quite well. If we're looking at this mining sample, and in this case, we want to identify the individual particles that are present with the sample, but not necessarily the individual phase compositions at the moment, we can actually get the sample quite accurately with something like a pixel-based tool or model. If we look at object-based models, though, we end up having an extra layer of power here, which is really important for this type of analysis. If we look back at our dog and our cat classes, not only do we get accurate classification within the dog class for these three dogs, but we also can separate them by instance. So we can see that this is one type of dog, a second, and a third. And even if they overlap or touch, we can still get that distinguishing. This becomes really important because if we look back at our two example cases, first starting with our low relief sample, we can see that using a object-based segmentation, now we can actually get individual identification of the different grains within this area. The same goes for our mining example. Instead of stopping at just identification of the particles themselves, we can see that now we can also identify the individual mineral phases within these particles as a whole. Now, some of you might be thinking, yes, AI is a great and powerful tool, but how can I actually start to use this, especially if I am not a computer scientist and I don't know how to code? And this is really where Zeiss comes in with its product line, because we know at Zeiss that deep learning is very powerful for image analysis. We want to allow our customers to be able to leverage it in an easy way, a way that's not challenging to implement, and also a way which can be easily conveyed to colleagues and to the community. As a result, we developed our own deep learning training platform with a goal to make deep learning accessible to anyone. With this platform, which is called Zeiss Cerebus Cloud, and actually all of the examples you will see today have used Zeiss Cerebus Cloud for their AI portion of their workflow. It is a platform specifically designed to make deep learning accessible to anyone. You do not need to know how to code, and you do not need to worry about expensive computing hardware to train your model. This product is based on a Zeiss-hosted Azure or cloud environment, which simply means you upload your images for your training to the platform. Then you annotate and define your ground truths, train your model. It will email you when the training's ready so you can inspect the model and update the training. We'll see how that works in a minute. And then when you're happy with the model, you can use it for segmentation and also segmentation of future data sets. Now let's take a look at how this works in practice. So to start, you upload your images to the platform and you define your classes. In this case, I have 7 different mineral classes. And what I can do is zoom in and start making my ground truths. Here, I'll do a chalcopyrite example. You see I painted, and it will fill in the object when I reach the end. I can then do the same to draw background around the object. I don't have to worry about painting close to the border because it can identify the class and account for that for me. And other than putting background right next to our objects, we also want to account for variability throughout the sample, things that are background and might not be captured there. I can do the same for minerals that have or particles which have multiple mineral classes in them. Here I'm annotating the first mineral class on this particle. Then I'm switching classes. And I'm annotating the second part. Once annotated, I then will draw background around this class as well. And what you'll see when I zoom out is I don't need to annotate the entire image. One benefit of our platform is you can annotate just areas of variability. You see here I account for my various classes and I click train. Training happens on our platform. I get an email when it's ready and I can inspect the results. And we can see how well the model's doing. Now, what this platform allows you to do is very easily train a model without needing a code, with just visual feedback and interface, and to account for all the variability in your samples. You can make annotations, then train, inspect the result like we saw at the end of that video, and add annotations in order to make corrections and teach the model in order to strengthen it. As the importance of training an AI model is as long as you account for the variability within your sample, and in that case I mean annotating ground truths for every single class, annotating in areas where the model mispredicted a class and correcting it, and also accounting for background variability, areas that look different from other sections, like here where we have a lot of crushed material, and accounting for background and illumination differences throughout your sample. So here our background's a little different than in this section. If you train a model and account for this variability, you can build a model that is robust enough to be applied to all of your samples and provide you with a nice result. Once happy with the model, it can then be downloaded and applied to all of your samples in batch, and you can work with the segmentations for your analysis and your end feature outputs. Now I'd like to pass to Rich, who will walk through some examples of using these AI techniques for different mineral analysis cases.
Thank you very much for the introduction to the Erebus software package, Molly. My name is Rich Taylor, and I'm going to take you through some geoscience examples of how we can use this new deep learning instant segmentation technology to do things we've just not been able to do before with our geoscience images and optical mineralogy in particular. So I just really want to focus on this difference and this shift that we're making from what was a semantic classification technique or semantic segmentation, where we based our image segmentation and our classification on what individual pixels look like. So we'd find some pixels of interest and then go and allow the software to find other pixels that look the same. It's a typical machine learning approach. And what we want to do is move away from this and use the advantages of this new instant segmentation, where our classification is now based on our object appearance. So that can be everything from the shapes of our materials and the difference between what the boundaries of those materials look like as we go from one grain to another, and what the inside of those individual grains look like. So it might be how they polish, or it might be their internal textures, or what micro inclusions look like that define what their appearance is. So this is a deep learning approach. It's dependent on good, or I should say appropriate training. So you've got to give it enough information to define what our materials look like. And it's much better for the kind of materials that we look at in geosciences, where there's lots of things that we use our brains very well for after we've been trained to look at light microscopy images, particularly where there's internal features within individual minerals that are very distinctive for that mineral type. So I'm really just going to take you through some quite simple examples of the kind of things that we tackle as geoscientists, but really things that just weren't even possible about a year ago that are suddenly becoming possible with this new technology. So just to show you this quick introduction, we've been using semantic segmentation for a long time. We use it across a lot of material science subject areas, but it really relies on this idea that the individual pixels that we're interested in are going to be significantly different from the pixels of things we're not interested in. And so if we want to highlight any kind of feature across all of these different types of examples, of which geoscience is just one. We can use these traditional semantic segmentation techniques, typically working best when we've got an object of interest and then the background, as we would call it. So the things we're not interested in. It can be much more difficult to use them for the wholesale characterization of everything within a sample, such as a thin section. So this is what we want to move away from, and we want to think about how we can use this object classification to be a much more useful tool for the geosciences. So here's a really nice example of something that'd be really difficult to tackle as a geoscientist doing some kind of automated image segmentation. This is a monomineralic sample. It's a marble. Where you can see there's lots of grains in here. These are calcite grains. Pretty much the entire sample is made up of calcite grains that are, broadly speaking, about the same size as each other. But there's individual features in there that are very distinctive that helps us understand their calcite that are part of the inside of each grain, the internal features of the grain. And then there's grain boundaries between each grain as well. And if we wanted to tackle this just from a pixel classification technique, by the time we'd selected enough pixels to define what a grain looked like in terms of its internal variation, which would essentially be the color and the brightness variation, if we used a semantic segmentation technique, our classification for this monomineralic sample would look like this. And it would give us the kind of things that we would expect from a semantic segmentation, which is the area proportions of the mineral of interest. In this case, for a monomineralic sample, it's 100% calcite. So it's done a correct analysis, but it's not very useful information to us in terms of geoscientists. We want to know the sizes and shapes of those grains, what the grain boundaries look like, how they interact with each other, how many neighbors they've got, all sorts of statistical analysis. So what we can do with the instant segmentation is go in there and use this software that Molly was showing, where we can individually paint grains to teach the software what grains of calcite look like in this sample. And in this case, we don't have to do a huge amount of training because we've got a relatively consistent sample in terms of the way that those grains look. And so you can see here, 10, 15, 20 grains going around, picking up some of the variation in size. And I've gone through this sample and highlighted, this is what grains look like. And by selecting the area here, it's telling the software, this is what the sizes and shapes of the grains are typically, but also it tells it that anything within inside that area is a natural part of the variation within a grain, whereas anything outside that area represents what the grain boundaries look like. So then when I run this through the software package, I get a result that looks something like this. It's taken that information and it can now segment the entire sample and say, these are all the different grains that I've found based on the training data that you've given me. And one of the things that's really important to notice here is that it's actually not segmented 100% of the grains. And you can see there's a grain here that's not been classified and another one next to it. It's classified almost all of the grains in this field of view. But the nature of the deep learning model is that these types of models are often not perfect, but are able to give us far more statistical information and to do it automatically than we've ever been able to gain by any kind of manual technique, such as point counting or manually drawing shapes. And so this is not about perfection. That's not the way deep learning models work, but it's being able to gain more information, more statistically representative information than we have before. If we get hundreds or even thousands of grains and miss 5 or 10 or 20 of them, then that isn't really a huge loss in terms of the statistical representation of all the grain size distribution here or information. And we can apply that then to a much larger image. We're looking at almost an entire thin section from the same sample here. And what we can see is, again, almost all of the grains have been classified with a very small amount of training. It would be possible to go and do another iteration and pick up on some of the things it missed. It might be a particular shape or it might be a particular grain size. What I've also been able to do here is you can see these yellow grains. These are still calcite, and we can see in the original thin section image, they're a finer grained region of calcite running through the middle of the thin section here. And I've actually told the training model that once we're below a certain grain size, I don't want to include them in my analysis. And again, this is a really interesting feature because I wouldn't be able to do this with semantic segmentation. Once I defined the pixel colors in a semantic segmentation that made up calcite as a classification, it would include all of those pixels as calcite. Whereas here, I can say, right, I want the bulk of my sample to be included in my grain size analysis, but those smaller calcite grains that make up these little sort of vein-like rivers through the sample, I don't want to include those. And that's a really cool feature of instance segmentation. It's because we're defining an object, we're defining what things look like. I can say that the same mineral below a certain size is not of interest to me. So moving on to a very different sample with a very different problem. Here we're looking at some microfossils, and we've got a single light microscopy image, a bright field image, looking at something that might be a marker horizon, for example, in like an oil and gas sample, or biostratigraphy sample. And these kind of things represent a really interesting challenge. And this is something where for people who look at samples like this, there is huge amounts of manual work to be done, going through and making sure we understand what features in terms of microfossils or other objects are present within the sample. And the reason this is so hard is because we're looking at something that's quite low relief, with lots of variation in it in terms of specks and flecks of other materials. But when we look close up and sort of increase the contrast a little bit, we can see that there's these little star-shaped fossils. There's discoaster samples. And there's lots of these. There's slightly different sizes. And the important thing is, in terms of their pixel color, if we were trying to use traditional semantic segmentation, is pretty much exactly the same as the background and all of the variation within the background. There's no way we'd be able to pick out these incredibly distinctive features with a traditional segmentation technique. But the important thing is, in terms of their features for instance segmentation, is they're very distinct objects. They've got a very distinct shape that we can use, and we can go in there and do some training again. In this case, I'm just picking out a specific type of feature, these little star-shaped microfossils, and saying, these are the things I'm interested in. You could pick multiple features out of this sample, multiple different species. And the nice thing is as well, even if these are slightly broken and they're missing limbs, then we can just still include these in our training. And then our model is going to count individual fossils that have got broken features or are only fragments, and still include those in the counting. And we can apply that back to our original sample. And in this case, it's able to say, right, there are 4,500 of those distinct things in there that you can look at. And again, it might be that there are variations here. If you are looking for different species of similar looking fossils, that is just something that you want to include in your training. You can say, right, I've got two different types of star-shaped fossil, and I can actually pull those apart by making sure that my training is appropriate for the problem that I'm trying to tackle. So this is the kind of thing that is able to go far beyond anything you can do with manual work or point counting. And you can also start to build up a database of different fossil morphologies in this case, and just have that as a library. So when you're tackling the same types of sample again, or looking for the same things, you can just say, right, I want to run these microfossil types through a set of new images and see if it picks up things that I've found before, or keep adding to those libraries just so your models are better trained and have got more information in terms of the variation of the types of feature that you're looking for. We can see when we look zoom in at the image that's now being classified, this has done a really good job of picking up those star-shaped fossils in there. As we scan around our sample, we can see it's barely missed any features at all, and found, as I said, about 4,500 of these in the original image. So once again, moving to a very different type of rock sample. This is now a high-grade metamorphic rock, a long way away from the microfossils that we were just looking at. But another really typical problem for light microscopy in geosciences that makes it really hard to automate segmentation routines, particularly for tasks that once we're trained, we find quite easy to look at. So in this case, we have a metagabbro. And one of the minerals in here is plagioclase, and this is a low relief mineral that makes up a fairly significant part of this image. You can see it here. It's this low relief pale grey mineral. And if we try to use a traditional semantic segmentation routine, it's quite distinctive, the plagioclase, in relation to the other minerals, these higher relief darker minerals such as the garnet and the pyroxenes. And we can do a relatively good job here of calculating the area proportion of plagioclase. On the right-hand side, we can see a semantic segmentation for the plagioclase. And for the most part, it's done a good job of highlighting those pixels. And there's a few small errors in here where the pixel classification has bled over into some other minerals. So it's not done a terrible job, but it's very limited information. It's simply the area proportion, roughly, of that mineral. But of course, we can add other layers into our light microscopy information. On the left-hand side here, Molly mentioned this briefly earlier, we can include a circular polarized light image. And for those of you who haven't used circular polarized light, it's a very useful image for segmentation, for polarized light microscopy, for geoscience samples. It's essentially the cross-polarized light information, but with none of our minerals in extinction. So we're always looking at essentially the highest birefringence color that we would be able to get for that grain in our sample. But this is really useful for segmentation because when we're looking at the same mineral and different grains of that same mineral in our sample in different orientations are in extinction or not in extinction, that means that the ability to segment the same phase when it can look so different, it can be black in one orientation and not black in another orientation, makes it incredibly difficult to use that incredibly functional cross-polarized light information, which we use all the time as geologists, in an automated way. Whereas a circular polarized light allows us to use that cross-polarized light information, but with any given mineral looking as similar to other grains of the same mineral within our sample. And so what we can see here on the left, our circular polarized light image now shows us the internal features, our twinning and our plagioclase, and very clearly got the boundaries between one grain and the next stuff. So we can start to do a similar process to what we're able to do in the calcite example, where we can train this model on individual plagioclase grains and say this is the expected internal variation of any grain, which is quite wide. Some of them are quite dark and they show the twinning. Some of them are more pale and don't show twinning. But we can give the model all that information and say this is what plagioclase looks like using both the plane polarized and this circular polarized image as multiple layers of information. And now when we apply our instant segmentation, we can see we've started to pull out multiple phases in here, including the garnet and some of the pyroxene and the plagioclase. We now do a much better job with the instant segmentation. We don't get a bleed over of the plagioclase into the garnet, for example. But on top of that, because we've included that circular polarized light layer, we can now see that we can pull out individual grains of plagioclase. So we can start to do things that we weren't able to do before. We can start to do grain size distributions or grain boundary information, anything we want to see about the junctions, these triple junctions here in this metamorphic rock. We can actually pull all that information out of segmentation straight from light microscopy without having to do any more high level or more expensive technique. This also means that one of the traditional challenges from pulling out mineralogy in light microscopy, which is low relief, colorless minerals in general, it's very difficult to do semantic segmentation for things like quartz, plagioclase, cordierite. If they're all in the same rock, we can use these multi-channel data sets and use quite subtle variations, which we're very good as humans to look at straight down a microscope and start to tell the difference between those minerals. We can train these models with enough information to pull apart these very similar looking minerals that have been very challenging for automation and segmentation. So another example I want to look at, which is a fantastically common type of challenge for a geoscientist. It's one of the first examples that we looked at with the Erebus software. And we can see here, this is an image looking in our Zen software at a thin section that had been made by a researcher of river sediment. And so he takes the river sediment and he mounts it in epoxy and makes thin sections and wants to do classed analysis. So he wants to know the sizes and shapes of these different clasts and what the rock types are, and look at things like how round they are and how broken up these fragments are to think about the transport of this river sediment. It's a relatively simple task, which if you want to use something like point counting across this sample, you'll be able to get the answers very easily once you're trained on these rock types and to do what is essentially lithology classification rather than mineralogy, but incredibly hard to automate based on that traditional semantic segmentation. And this is the reason why, when we look at what we might be able to do with those kind of clasts with semantic segmentation, we can train our machine learning model to recognize things like quartz. And we can see that there's quartz in almost all of these clasts in different sizes and shapes, or I would say pale transparent minerals in here. Some of them might be quartz, some of them might be feldspar, that make it very easy for us to see that these clasts are different. So these dark clasts have a very small amount of pale transparent minerals. These clasts have a larger proportion and they're coarser grained. But if we try to use semantic segmentation effectively on light, dark, and sort of medium colored minerals, we'd get an image like this on the right, which starts to give us a breakdown of that variation, but doesn't actually tell us the difference between the different lithologies. We can visually see that this class that's mostly orange here is probably similar rock type to this one next to it. But in terms of the semantic segmentation itself, all it's got across the entire sample is the proportion of orange and the proportion of blue. It doesn't recognize that this grain up here that's mostly pale blue is different to this one. It only recognizes that there's a lot of blue or not very much blue in different parts of the image. So this is not very useful information for the researcher who wants to do lithology classification, because semantic segmentation effectively at this point is just showing us variation in mineralogy and not lithology. So what we can do is use the Arebus software. So we can think about our objects. First of all, we know we want to be able to measure things. So sizes, shapes, roundness, sphericity, aspect ratios, all of these things. And so we can define what our objects are and what our backgrounds are. And we can see very quickly, we're able to say, based on the image, what an object is and what a background is. And we can measure all of the class based on that information. And I think Molly showed earlier, this is fairly easy to do in the software. So we can just come in and say, right, these are our objects, these mineral class. And once I've defined enough of them, covering enough different rock types, and define the background, it's going to be very easy for the software to say, here's all of your things that you want to measure. And I can bring those into our software and get all that information that I want. It might be areas, in this case, circularity, compactness, and any different statistical measurement of these objects that we want. What we want to do now is go back through a second loop in our software and train it on different lithologies. And that's a very easy step, as we could just go through the same process that we went through earlier for the calcite grains or whatever else. We go in and we draw over these different class and say, right, these guys that are predominantly dark are going to be my first rock type. You can break this up into as many different classifications as you like. And then we can train the software to say these things are not just objects, all these class, but there's different types of class as well. So now it's not actually that interested on the right-hand side here on the internal variation of any individual class itself. It's just saying that internal variation all counts as one type of thing. And so that might be, in this case, we can see quite altered rocks with veins and things like that. They can get pulled out. All of that complexity gets pulled out as one object, and it'll find other things that are similar to that. And all of these different lithologies, whether they're more mafic rocks or intermediate rocks or felsic rocks, are getting classified based on all of that internal variation and what that looks like as an entire object. The final example I want to show you really takes us into a slightly different workflow that's actually really important in the geosciences, and something that we've been talking about a lot for many years, which is how well can we start to think about doing automated mineralogy with our simplest analytical technique, which is light microscopy. We do automated mineralogy using a scanning electron microscope, typically with EDS, so doing chemical analysis. And we do it in 3 dimensions as well. We can use CT scanners now to do quantitative mineral identification in 3D. But those are both relatively expensive instruments and techniques. And we want to be able to use light microscopy to try and do a similar job. And this has never really been possible. And part of that reason is the classification technique that we've had. So that semantic segmentation technology has never been very good at really consistently tackling multiple samples and being able to understand or being able to apply those classifications that we created in one sample and apply them to another sample. Not just because we might have some variation from sample to sample, but if our sample is prepared in a slightly different way, for example, and we get different surface roughness, and if we have too many minerals that are very similar to each other in terms of their pixel colors, then there's not enough information there to differentiate our different minerals. So we've got a nice example here. So a typical example we might put inside the SEM for EDS automated mineralogy. And I want to show you a little bit about how we can use our instant segmentation to do a better job of turning an image like this, which is a reflected light image for ore mineralogy from a copper mine, into something like this, a fully classified image that we can do not just mineral identification and mineral grain analysis on, but also particle analysis at the same time, which is a really important aspect of our process mineralogy workflow. So the process itself is exactly the same as everything that we have seen so far. But what we're going to do is take this through a couple of those steps that we've talked about in terms of object and mineral classification, in terms of the statistical analysis. And actually what we're doing here is building together a little work package that enables you to build up any number of mineral classifications and automate that workflow. So we can start to make this easy. And you can build up these libraries of minerals that are relevant to you and use those for this automated mineralogy workflow. But the thing that's really important here is that this change from the semantic segmentation, where we're just looking at pixel colors for lots of these minerals, lots of examples that might include faces like this, for example, in reflected light. We know that most of our reflected light minerals come up in some shade of yellows or some shade of grays with a few variations. There's not enough information to differentiate those things or to find the edges of grains and find the edges of particles very neatly using those traditional machine learning techniques. But this shift to the deep learning and the object classification enables us to get incredibly neat classifications, and we can see how good the edges are on each of these grains and particles here. And part of this is to do with that initial training to look at the background, which in this case is epoxy, but also because that instant segmentation is taking in all of the variation that it sees, not just the pixel colors, but also across any given object that we've trained it. It can look at the internal texture. So that might be the way that samples polish, the way that they pit. So things like galena, for example, with those triangular pits, that can all be incorporated into some of the features that this model is going to look for to say that that is galena, or the sort of slightly more pillowy texture of something like arsenopyrite, as well as the color variation. Those kind of internal textural variations are going to get taken into account. And that includes also the way that they fragment as they're crushed. So particular sizes and shapes of different grains are all going to get incorporated into that model. And this is enough information to start to neatly separate minerals, even when the colors themselves might be very similar to each other. And so we can see, we can start to pull out statistical information here from, in this case, an individual grain. It's a single mineral. We can pull out a single mineral across the entire sample and look at something, any kind of global statistic, in this case, surface area for the chalcopyrite in the sample. But most importantly, we're not just able to separate out the different mineral grains, but the key feature of this software workflow to do automated mineralogy is if we look in the center here, we've got a large particle that's made up out of two different minerals, in this case, chalcopyrite and sphalerite. And we need to be able to measure all the statistics of that individual particle, as well as the information about the individual minerals that make up the grains within that particle. And by using this segmentation technique, we're able to generate that information as just as a part of automated routine workflow, because our boundaries are incredibly neat and accurate, and it's taking all that information in to generate the model. And so when we combine this with a way of automating the data acquisition, So something like the ActioScan, we can start to load 100 thin sections in here. We can generate huge amounts of light microscopy data very quickly, whether it's in transmitted light or reflected light, and then apply these models across multiple samples or batches of samples over days, weeks, months, and generate these automated workflows that are really important for the industry side, as well as all those things that are really neat for the research side as well. And the nice thing is that really changes from semantic to instant segmentation is the semantic segmentation was really reliant on seeing the same mineralogy. So if I wanted to build a 3-mineral classification based on semantic segmentation routine for a thin section that had those 3 minerals in it, if I then had a 4th mineral in a new sample, I wouldn't be able to use that old model. It would try and absorb that 4th mineral somehow into whichever is the nearest classification. Whereas the neat thing about these instant segmentation techniques is you can either pull out individual minerals from an old model. You might have had 4 minerals over there. You want to use 2 of those same classifications in an entirely new model with a bunch of different minerals. That works just as easily. You don't have to start again just because I've got a new combination of minerals in a sample. So just to finish up, I just want to talk about some of the things that we've covered and some of the things that are important here. This idea of shifting to instant segmentation is incredibly important for geologists. We care a lot about the way things look, the texture of samples, and their internal features. It's how we've been trained to understand light microscopy images. It's a huge amount of information. We look at on something like a rotating stage optical microscope in polarized light to understand very subtle differences between different minerals. And finally, we have a segmentation tool that's taking on board all of that information that we're used to using. The other thing that's really important is that these tools are becoming much more prevalent, and we're going to be using them. Like there's no point in shying away from them. We need to take these on and start to apply these techniques. It's going to enable us to be much more consistent across the analysis of our samples. And by being more consistent, we can build bigger data sets using those consistent techniques. That means we have genuine big data that can start to be tackled as large databases and look at what's happening in tens, hundreds, thousands, hundreds of thousands of thin sections or samples, whatever it is that you're looking at, and apply these techniques. Not just, hopefully I've given you an idea of the kind of things that we could tackle, but you could use this kind of image analysis for anything where the shapes are of interest, whether it's stereo microscope images of fossils for hand picking, it could be fold structures in field photographs. All of these things are just shapes that can be trained and classified and then applied to larger image sets and to look at the things that you're interested in. So we have a lot of benefits based on these large numbers of parameters that are in our model. It's incredibly simple and intuitive to use. We have a huge development in the number of AI tools that we're using at the moment across all of our microscopy techniques. And the really important thing is that they shouldn't be difficult to use. These ideas of just painting your sample and clicking on the objects that you're interested in and allowing the software to do all the hard work is really important. There's also far fewer limitations, where we always found that we needed a very specific task for the traditional machine learning techniques, where we now are able to tackle much more generic tasks. We're going beyond simple mineralogy into understanding lithologies and textures of our samples. And as I said, these classification techniques are much better at saying no to things. The traditional techniques, semantic segmentation, for example, however many classifications you gave it, it would then just try and classify 100% of your sample and fit everything to the model that you've given. Whereas here, with this instant segmentation, it's much easier to build in that kind of confidence level to say, right, I've got a thing that doesn't match any of the classifications, so I'm just not going to classify it. And that's what enables these things to also be much more transferable. So hopefully I've given you a flavor of the kind of things that are possible, and you can think about the examples that I've shown you and think about how you would apply them to your own samples and your own problems across light microscopy and other image types too. Thank you very much for listening.
Okay, so we're back in the room, as they say. Thank you ever so much to our expert speakers. And Rich has indeed joined us now for the live Q&A segment. My name is Chris Parmenter. I was introduced by our AI introducer at the start. And I'm here to moderate the Q&A. We've had lots of really interesting questions. And can I say for my part, I really enjoyed what we've just seen. I hope you all enjoyed it out there. We've got about 15 minutes, so let's just jump straight in. Rich, question to you then. How much time, you made it look very easy, but how much time is actually spent training the models compared to running the models with a new sample?
Thanks, Chris. That's a very good question. Really, there's no right answer to that question, because it really depends on what you're trying to achieve and the complexity of the objects in your image and how many different types of object you're interested in classifying, and then of course the resolution of the images and therefore the sort of file sizes that are involved. I think we really tried to bring across that the training itself is quite easy. So what we would usually do is, if for example we have a large image that we want to classify, or multiple large images, we then crop out small areas of that. So we might have 5 or 10 small images from different regions to try and pick up the variability. We then do our classifications on those small subset images, so the training can happen quite fast. And then once we're happy, when we get that sort of feedback from the system to see how it classifies those small cropped areas, once we're confident that we're doing the right thing, we might go and segment the sort of main image, which would be a larger file size. So I showed the example of the calcite. That was about 15 minutes of time I put into that as a single mineral. The amount of shape variability was fairly small. So once I'd given it, 20 grains, whatever it was, it sort of knew what it was looking at, and then it probably classified something like 95% of the grains in the image.
Wow.
If you've got a lot of variation and a lot of phases, a lot of different grain sizes, you have to sort of change your thinking a little bit. So if you've got something relatively simple like quartz or something like that, but lots of different grain sizes and shapes, just telling it that light colored mineral is quartz doesn't necessarily mean it's going to find other quartz grains very easily. Because if you train it all on small grains and then there are big irregular grains, it doesn't know those shapes in the training.
Sure.
So the more variation, the more training time. But that's usually then what takes the most amount of time. Segmenting the images themselves is pretty quick. So you could spend anywhere from minutes to hours sort of training your image and getting confident, and then tens of minutes segmenting your images.
And if you find, once you've done your initial training, that it's not doing a very good job, as I understand it, correct me if I'm wrong, that you can kind of give it a nudge in the right direction and retrain it and sort of say, right, okay, you did a pretty good job, but maybe you might want to consider this, and then it learns that, right, and it gets better.
Absolutely. And so as with all segmentation training, really it's an iterative process where you want to start off with some simple ideas and just train it and see where it's at, and that's usually the best way of doing things. And then you can go back and add in extra phases or different sizes and shapes of the phases that you've trained. And importantly, the way that the cloud system works is it saves every iteration that you've done as its own setup. So if you do something terrible, you can always roll back a few models, or you can give a model to someone else, and they might be looking at quartz and metamorphic rocks, and you've trained it all on very equigranular looking quartz, and theirs is all elongate, so they can take your basic quartz classification and add in shapes that are relevant to them. Right. So it's really very flexible what you see in the software and how you can update models.
Okay, cool. So that answers another question we have here. Can I use other models that other people have made? So the answer, I guess, is yes. You can take something that someone else has made with their permission, or is it kind of like when everybody uploads these things, we're all just giving permission for other users to kind of use something that we've already got?
So you're absolutely right. We can share models. Because all of this is being done in a cloud-based setup, which makes it very easy, and it makes the sharing very easy, because it works a little bit like how you do all your file sharing within your work or within your university. So I can go into my my Revis setup, and there'll be a menu for all my files, a menu for all my models, a menu for all my segmentations. I can go into the models, and this is what I do with Molly when we're working together on this stuff. And I say, right, here's a model I've just done. Share with I find Molly's email address, it'll ping her an email saying Rich has shared this file
Okay,
with
so
you.
you're actively giving her permission and consent to right. Okay.
And she can then use that model, or she can use it as a basis to expand on and turn it into something that's more detailed or whatever.
Right.
So that's that's how we built the mineralogy model at the end. Is she worked on the object classification of just what are the objects and what are the backgrounds, while I worked on the mineralogy, and then we built this sort of two layered approach where it can get the sizes and shapes of all the particles, and then obviously Molly's not a geologist, but she's the AI expert, so I was then putting in the mineral names and the mineral classifications on top as a layer.
So it becomes a truly collaborative sort of activity. Yeah,
that's the idea. And because of the way that it works, explained a little bit at the end, where you can actually pull individual components out of these models. So the way that it used to be is if you had a certain combination, you could only use that model in that combination. Whereas now I can pull out a mineral and give it to somebody else. And the way that, well, I say the way that it's going, the way that I would like to see this go is that this is then a capability of community-led quality control on all of these systems. Everybody can effectively, if you want them to, have access to the models you're using, doing your classifications. They can test it out. They can benchmark it against things that they're doing. And that's the way that this should be. Once we're getting to this point where we're generating so much data and using these slightly black box tools, the most important thing we can do is make sure everyone's able to use your method and check that it's doing what you say it's doing.
Okay, cool. Wow. I mean, and this is very exciting. I think obviously this is around geology, but I'm guessing these tools can be applied to other types of microscopy, because obviously you were applying this to mostly light microscopy images.
Yeah.
But you could apply them to other types of microscopy as well. And I think you might have mentioned X-ray as well.
Yes, absolutely. So the reason that we focused on light microscopy here is because that is the subject area we've had the most difficulty automating as geologists so far. Whereas we have, so for the SEM, for example, we use EDS, and that chemical classification is a really powerful tool. Whereas light microscopy, we've never really had anything that gave us the information we really needed, and that's what the big shift is here. But absolutely, this software doesn't care what images you put into it. It can be slices of a 3D stack of images that are then used to build a 3D segmentation. The life science guys at Zeiss use this for live cell imaging. So on that have got time slices, so you can segment one time slice and then track those objects through time once it's done the segmentation, and give you pathways of moving material. Once you understand that you're creating objects, it actually doesn't even care if they're moving from image to image. You can start to build that in as well.
Wow. Okay. And so another question then, what kind of hardware do you need to train the models? I think it's fairly minimal. Is that right? Because it's all in the cloud?
Yes. And that's a very important comment. And it's good that it came up, is that the real grunt that's needed is for training the models. And that all happens at the Arevis end. So you log in through a web browser to your account with Arevis, you upload your images, you do your training, and then it's that model training that's very intensive from a GPU perspective.
Right.
But then what you can do is either use that cloud software to also do your segmentations, or once that model's trained, you can pull it down to a relatively normal workstation and use those models for segmentation on a PC that you've got. But the really intensive model training stuff that requires a lot of grunt, that's all done at our end. That's all done using that cloud interface on a web browser.
Okay. So the software is Arevis. It sort of runs in the cloud. You can feed it the images of any kind of description. This is, and then it spits out a model that you can then apply to segment whatever it is you want to segment. It almost sounds too good to be true.
You can give it faces and tell it that the objects you're interested in are eyes. It doesn't care that they're microscopy images.
Right. Okay. So obviously you mentioned you've kind of you spend 15 minutes or you can spend an hour. How many particles have to be analyzed before you get your results kind of stabilizing? And I think we saw a little bit where you were doing one and doing another, and it almost started to do it kind of as it went along. So how many particles do you need to feed it before it starts to kind of get the message and starts to stabilize the the, I guess, thresholding or segmenting?
That's a good question. I guess the reality of the answer there is that that's a statistical problem related to the material you're analyzing rather than the technique you're using. So, so the way that you would think about the number of particles that you need to analyze. So I think that's probably the question is referring to the reflected light image at the end, where we're doing the particle and grain analysis. You would think about that in the exact same way as you would do if you were using the SEM to look at those particles with EDS-based automated mineralogy. And you know, there's lots of papers on at this grain size with this many phases, you need to look at this much material before you get a statistical likelihood of a good answer. But it's going to be dependent on everything from grain size to, you know, the size of the phases of interest to how well it's crushed, and so how many particles you've got in, you know, one image. So that the answer to that is going to be different for different people's samples. But the important thing here is, and this is how, again, it relates to what we've been able to do for a long time on the SEM, is that you build this consistent library that you can just apply to more and more images of the same material. So, and also you can see if it's choosing not to classify something, that's telling you, it'll be like, you've got objects in here. I can see that based on the object background, but I don't have a mineral classification for them. So something new has appeared in your mineralogy that you didn't have before. So that's very powerful too. But yeah, there's no right answer there. I mean, that is, once you've done that training, you know, there was, I think, 6 phases in that sample. It was a copper ore, a fairly standard copper ore, concentrate from a mining company, and we'd done training over a small number of areas, and then it's gone and analyzed 20,000 particles or something. So the point is that you're able to automate these processes to a level of statistics that we just weren't really able to do with light microscopy. We've only been able to do it with greater techniques. But for some people, the answer to that question might be 500 particles, and for some people it might be, you know, 100,000 particles. It depends on the material's complexity and grain size and everything else.
Sure. Okay, cool. I'm just reading through the questions while you were just talking. There are so many questions, guys. Everyone seems to really gotten really excited about this. Let me fire a couple more over to you because we've got only a couple of minutes. I think this one, can we upload pictures taken by different microscopes to the software, or must pictures be taken by the same microscope connected to the program? That's a general question, and I think the answer is it kind of doesn't matter in one sense.
Yes. So very short answer to that question. It's a web browser interface where you're uploading whatever image you want. So all the images we looked at were geoscience slides. It's been scanned on an Axioscan, so an automated slide scanning system. But they could be your photographs from your holiday. It could be.
But it is an interesting question, though. But because if you had someone who did some, say, microscopy of any description, whether it's SEM or light microscopy or whatever, and then did maybe a follow-up piece of work on a different microscope, that would kind of matter, or it wouldn't necessarily matter. Would the difference be something that the program would take into consideration? Would you have to retrain it to say, oh, this has come from I mean, obviously we're not comparing light microscopy with SEM, but if you had the same sample or a similar sample taken on 2 different SEMs, would that matter?
Not really. I mean, the thing that you have to, I guess that question is leading into a correlative microscopy idea. And the important thing to remember, if you want to compare any technique or build up layers of information from different techniques, the important thing you have to do is have a pathway to segmented data. And so once you've got segmented data, you can measure anything you like. So I think somebody asked a question about, you know, what are the measurements that come out? That doesn't matter. Once you've got segmented data, you can choose any parameter of size, shape, circularity, sphericity, aspect ratios, or whatever. And we've been able to do that segmentation with an SEM to get all that information. And now we can do it very accurately with the light microscopy as well. And what you would then do is in a different bit of software is say, right, I've done my light microscopy segmentation with a Revis. I've got some SEM segmentation from EDS detectors, and I bring those together in a correlative workflow where I can then start to combine information.
Okay. So 2 more questions very quickly. Somebody has asked, can we include chemical analysis, for example, from EPMA? So I'm guessing the answer is yes, because you've just mentioned EDS.
Yes, but it would be part of a correlative workflow. So we take the
Right.
data that we extract from this method and bring it into a
Yeah.
correlative software package.
Okay, cool. And then the final question, because I think I'm going to be running out of time here. What is the smallest size of grain or crystal, microns or millimeters, that can be considered or used? So is there a lower limit to what you could work with?
That the only limitation is the resolution of the image you're willing to upload. So if you can't see the features based on the image resolution, quite often with the light microscopy images, they could be massive files.
Yes.
It's one of our most intense file size techniques. We tend to downsample them. If you care about really fine particles, then don't. If you can't see them in light microscopy, you might need to use electron microscopy instead and see things that are smaller. But effectively, if you can see it in the images at the resolution you care about, then
if it represented a couple of pixels, or if let's say 10 pixels or something, as long as you can define that area, then the model will know, oh, it should be this size, this shape, it should have maybe this intensity or whatever it is, because you're telling it that information at the start.
Yeah, I mean, possibly more than a few pixels, but as long as you can define clearly enough the shape of it distinct from something else, the shape and the color and all the other properties, then yeah.
Sure.
But as is always the case with any microscopy technique, if the resolution isn't there for your problem, then you need to use a different technique, and then.
Well, of course. I'm just thinking this is going to be hugely. Obviously there'll be, as you say, slightly different questions being asked by different people and different techniques being used. But essentially, it's going to be great. I just wish that everybody knew about this. Clearly, this is the point. So if you have enjoyed this webinar, tell your friends. Rich, we've run out of time. Thank you ever so much. It's been great. It's been a real eye-opener into the future of what can be done in terms of using AI, especially for those of us who are not coding experts. So thank you for your time. And I hope everyone watching has enjoyed it. I believe this will be on demand. So if you've enjoyed it, tell your friends, or if you want to check back and note down some of the details, then rewatch it. And I wish everybody a good day wherever you are in the world.